This video just gives an overview of a recent paper that Helen and I have published that contains a framework we've been discussing for a while, and hopefully I'll just sort of talk briefly through that framework and how it's come about over the next few minutes or so. So it's quite common in sports biomechanics for all of us to try and understand an athlete's technique and to identify features of that are important for performance outcome. That's a fundamental sort of concept in sports biomechanics. And obviously a very long-standing one that many excellent people and experts have written some brilliant pieces on, as we hopefully discuss in the introduction to our paper. The whole concept of technique and the whole sort of range of complexities in the measurement, the processing of data that are intended to quantify specific aspects have been, discussed at length. There's some excellent work back from Adrian Lees, Fred Eden, others that we touch on that talk about the many complexities in this. But also there's lots of work in the process for how we then relate those features of technique to the performance outcome measure. And again, lots of great work in this space around the various methods that can be employed and kind of have been employed to attempt to relate these features of technique to the observed or the predicted performance outcomes. And that might be whether we choose empirical, experimental, theoretical approaches as our sort of research designs to do that, or it might relate to the statistical or more recently sort of machine learning type approaches that are used to relate those inputs, the technique features, to the outputs that are the performance outcome. But again, there's lots of great work in that space, as we hopefully touch on in the introduction to our paper. Where there's less work, and I think this is a really important point, is that the actual performance outcome measure itself often receives relatively little attention. And even in much of James Hayes' early deterministic model work, it's the top box in these deterministic models is a really important consideration, but it's often only touched on very briefly. And that's what this framework is hopefully all about supporting, is how do we identify the most appropriate measure to use as our performance outcome measure. Now, this general concept is something that I guess has been sort of going in and out of my head for several years since I started my PhD just over 20 years ago. And it was because of the sprint start that I first kind of came across this challenge ultimately. So in the sprint start, block velocity had typically been used as the performance measure, the horizontal velocity of the athlete's center of mass as they exit the blocks. And not going to go too much into the details, there's bits in the paper and in these other papers as well. That's determined by impulse, which is a function of force and time. So athletes could get a good performance outcome through producing more force, as would be ideal, or also through spending more time producing that same force, which goes against the nature of kind of sprinting, i.e., getting to the finish in less time. So when you dig into that, much of the early work that looked at set position block spacings in sprinting tended to favor more elongated block spacings for performance. But ultimately, they were biased by the performance measure they'd used, favoring those for producing more impulse, higher block velocities. And that's what led to the kind of start of this work in sprinting. And then probably because of my sort of interest and awareness of that with PhD students, so Alex and Sam, as you can see on the screen here, when they started out on projects with different sports, one of the early things was considering the potential biases in the performance measures used and whether alternative ones needed to be used. And you can see a couple of papers that they both did as the start of their PhDs on this topic. And it was when I started to reflect on these and the sort of the commonalities and also the differences between them that I kind of roped Helen into helping get this out of my head and into hopefully something useful for others, which is where this framework has come from, really. So I'll just spend a couple of minutes going through the framework. The paper write-up uses examples from these three papers and a few other hypothetical ones as well to hopefully illustrate the different steps. But I'll just touch on it briefly to give a flavour of it now before hopefully you dip into the paper if you choose. The framework itself is sort of fundamentally split into two main parts. So the first part of it is considering the potential sort of conceptual biases so that you can identify what the ideal measure might be. And the important thing here is it does relate to the question and the perspective from which that's being framed. And we touch on that a bit more in the paper about what we mean by that quite broad idea of a perspective. And then once you've identified the ideal measure, it's important to obviously assess the measurement properties, think about how you can obtain it, whether it's sufficiently accurate, and therefore whether it's suitable for application. So the framework itself is sort of split into 7 different steps. And I'm just going to touch on them very briefly, and obviously more details on each of them are included in the paper. First of all, we're not talking about reinventing the wheel unnecessarily. If the performance measure of the sport is the ideal for that question you've got, then obviously use it. Sometimes that's the case, but often as biomechanists, we are looking at sort of sub-phases within a sport or isolated movements or tasks within a broader sport. So actually, it's not as common as you might think that the performance measure of the sport is the ideal one. And the framework sort of works through this essentially kind of yes-no logic. So if it isn't the ideal measure, again, we are not trying to reinvent the wheel. Are any other measures that are either officially used in practice or established in research, or both, for example, available that could be used for this? And the swim start's quite a nice example here. So if we're interested in dive technique off the blocks in competition, you get a block time measure as well. And time to 15 meters is often widely used in practice. But if we're solely interested in the dive performance off the blocks, both of those come with their biases, as we touch on a bit more in the paper. So it wouldn't be ideal for just looking at way an athlete dives off the blocks. So if those do exist, that's where we're getting into assessing whether those are ideal for the question. If others don't exist, or if they're not ideal for the question, it then becomes a bit more of a conceptual challenge. What is the ideal performance measure? And sometimes that's a slightly different way of looking at the question, as we touch on with the rowing example that's included in the paper. Ultimately, when you've identified the ideal measure, we then move into this assessment of its properties. So firstly, can you directly measure it? And that is based on the constraints that you're operating within. So within the environment you're in, the instrumentation you've got, the concept itself, as I touched on in the rowing example a little bit. Again, it's quite situation specific, this. There may be some instances where you do have, for example, access to instrumented starting blocks and you can measure forces, but in an applied environment with limited access to athletes or limited use of those blocks, it may not be possible. And if it's not, can we indirectly calculate or determine it? And Alex's rugby paper is a nice example here, where we wanted to track the full flight path of the ball to see whether it would have cleared the posts and gone between the uprights. But the work was done in the lab, so we could get more accurate measurements of some of the technical features. So we couldn't track the ball path, but we could get all of the necessary inputs and actually have an aerodynamic model that predicted that ball flight path. So you could indirectly calculate it from the data that could be obtained. But obviously, if doing that, and also if we can directly measure it, we need to be very clear and careful about our measurement errors. Are we measuring it with sufficient accuracy for the current purpose? And again, the context is important there. What are we intending to use it for? What are the expected differences or changes that we might be able to detect? And how do those compare to what we would need to be able to detect as well? And if it is acceptable, then of course, brilliant, we can use it. But important to report those measurement errors and report still probably some biases that likely might be there in our choice of measure, because very few are going to be completely unbiased in their assessment of performance. If those measurement errors aren't acceptable, or if we can't indirectly calculate it, there is sort of this option outside the framework to iterate back if other potential measures exist that weren't ideal but were alternatives, and kind of select the next most ideal one and go back into that loop in the top half and then back down into step 5 again. But if we get to the point where we start to exhaust all those potential measures, ultimately then for that particular question, we can't measure the construct of performance appropriately, i.e. either with sufficient accuracy or actually in a sufficiently unbiased way. So it becomes a bit sort of futile or pointless to actually aim to do so. So it's just an important consideration of making sure that our performance measure that we use is the most appropriate one, both in terms of its sort of biases and its concept, if you like, but also the accuracy with which we can obtain it for the application we're using it for. So very much a whistle-stop tour. There's a QR code that links to the paper. There is available open access in sports biomechanics. So hopefully will be of interest if this type of stuff is relevant. And hopefully it will kind of make you think about the performance measures that you do use in sports biomechanics applications. As we said, definitely not a need to reinvent the wheel unnecessarily. But even if not, it just helps you think about the measure you're using, critique it, understand its biases, its limitations, and see whether alternative ones might be worth considering for different applications.